then let's start. Okay. Valeska is in, and first of all, I want to follow up previous session, and there was a question from Valeska. Well, we talk about the difference between mixed effect and GEE model, and the question from Valeska was why the coefficient estimation from GEE is always less as compared to mixed model, if you remember. And to answer to that question more systematically, I'm going to present a little bit before I go to today's main session. And I created simulated data of 5 clusters and 100 records on 2 variables, X and Y per cluster. So we have sample size of 500 because 10 observations per cluster and there are 5 clusters. And Y is a binary outcome and X is continuous covariate. And well, this is this explains the data set. Maybe it's a bit confusing, but this one shows histogram. Well, the bottom one shows a histogram, well, counting the number of records when Y is equal to 0. And the above, this is also histogram, but yeah, it's vertically flipped when Y is equal to 1. By the way, I'm using cursor, but can you see my cursor on the screen? Okay, so this one, for example, in cluster 1 up to 20, well, no, 25, all the observation had Y equals 0. And starting from 25, we started have observation of Y equal 1. And then after 40, all the observation were Y equal 1. Okay. And when we look at cluster 5, all the at the low value of X, all the observation had Y equals 0. And then I think from 60, we started have observation with Y equal 1, and the number of counts increases as X increases. And after 71, all the observation had X equal 1. Okay. And then we fit mixed model. And this is what we get as a estimated mean value. So for cluster 1, the probability of having Y equal 1 is kind of 0. And after 20, it starts increasing, right? And then going up, and then probability of having Y equal 1 is almost 100% when it reaches to X equal 50, which is somehow consistent with what we observe here. And the same thing for cluster 2, cluster 3, 4, and 5. Okay. And what we get as a mean component, this is what we get, I mean, as an overall, or I should say average effect of X on probability of having Y equal 1. And then how about GEE? In case of this one is probability in probability scale from 0 to 1. And when we change to logit scale, in logit scale, these are lines we estimated, and each line represents each cluster, and the dotted line represent overall mean. And how about GE? In case of GE, well, we are interested in population average. So when it doesn't consider cluster specific distribution of Y equals 0 and Y equals 1, but it considers a distribution of Y at population level. Like here, we're up to 20, up to 25, we have all records with Y equals 1, Y equals 0, and after 20, we started having records with y equal 1. And then after 75, we start having only records with y equal 1. And when we fit GE, this gray line is a predicted or estimated mean. As you can see, this slope is less steep as compared to the one we saw when we used a mixed model. And this is in logit scale, and the same thing as compared to slope we found in mixed model, the slope from GE model is less steep. And what do we estimate from this model? We estimate the slope of this line. And this is a reason why the coefficient from GE is always smaller as compared to mixed model. And I wonder if it is clearer than what I explained last time. Do you have any question? Okay, I don't hear anything. So this is a recap of what I explained a little bit after I received question from Barista. And today's topic is okay, this one. So how to do exploratory data analysis with correlated data. In case of linear model, this is a topic we are going to cover. In addition to EDA, I'm going to talk about shrinkage estimation and ICC, interclass correlation. I think everyone is familiar with ICC, I guess. And many research, well, some researcher presents ICC from their study. And among participants, have you ever heard this shrinkage? If you have asked, you have heard, please raise your hand. Well, I don't see any hands. Okay, all right, so we will talk about shrinkage information. And you may hear shrinkage when we talk about a mixed effect model, and I'm going to talk about it. And today, we focus on multi-level analysis, not longitudinal analysis. And this means that we assume the correlation of response or outcome variable is constant across clusters, which is not true in case of longitudinal data analysis. And we need to do more assessment for longitudinal analysis than what I'm going to show today. And also, we are going to focus on linear model. And today we are not going to touch on logistic or Poisson negative binomial model today, and I'm going to cover next time. So what are the contents of exploratory data analysis when we have clustered data? First of all, we have to look at clustering or nesting structure. And also we have to check mean component, which is a crude observed or unadjusted association between outcome or response variable versus covariates and predictor you are thinking in your model. And thirdly, we need to assess the variance component. Namely, we have to look at the crude observed and unobserved between cluster and within cluster variation. So basically, I say so. Well, what we need to check is not totally different from regular regression. The first one is somehow specific to multi-level data. And well, the second one, this is what we always do. What we always do when we do any regression analysis, we want to know if there is if we can assume that linear association holds. So this is exactly the same as regular regression. And the second one, we check when we do linear regression, we check that if the variance is constant across each value of x. This is what we check. And this is similar to us for multi-level analysis, but we have two levels between cluster and within cluster variation. So this is the difference between usual and these multi-level cases. But what we need to check, they are not totally different from regular regression. And today we are going to use example data, and you can find this in the Google Drive so that you can explore if you want to. And I'm using simulated data set based on Saluba data set from Mexican Ensanut data set in year 2016 for adult population with 16 years or above. And sample size is about 4,000. And this data set includes these variables. And session studies aim is to assess BMI in relation to sex, age, and population size, accounting for clustering at city level, which is L180. By the way, this data set is simulated, meaning that I change the value and I change the value for city ID so that we can include data confidentiality. So don't use this data set for your analysis because this is a fake data set just for this purpose. Okay, first of all, let's look at this clustering or nesting structure. And this table shows a number of observations per city. First of all, here we see that the number of cities is 59. And then look at this part. This is somehow notable. Smallest, but so the smallest in terms of number of observations per city. So the smallest city contains only 7 observations or 7 individuals per city. And the second smallest for 10 individuals per city and so on. And then 50 percentile, which is median, is 39 individuals per city. So it's kind of small, as you can see. Well, if you want to get the city, if you want to get the city estimate, well, we don't have, I say, city representable sample because the number of sample is very small. Then this is what we can get from this table. And we have to keep in our mind. And also, using this histogram, I plotted the frequency of number of observation per city. And we can get to know that, there are many cities with sample size below 50. Okay. And there's one city for which we have huge amount of records. We have about, I think, 900 or 959. So about 1,000 records per city. So there is kind of difference in terms of number of records per city in our data set. And this is also we want to keep in our mind in our analysis. So the summary, assessment of clustering nesting structure. First, we check the number of cluster, number of units per cluster, and how multiple layers clusters are nested. In our example, we have only 2 levels, individual and city, and sometimes we have more layers. We may have sub-cities or we may have country level. In this case, we have multiple layers and we want to look at the nesting structure between layers. And why do we do that? First of all, we want to know the data better. And we want to know how many countries do I have, how many cities or sub-cities per country do we have, and how many individual records we have per city or per subcity. And secondly, we want to identify if there are any small sample problems, like too small number of clusters or too small number of units within the cluster, which was the case in case of this data set. And well, if the number of units is too small per cluster, our estimation is going to be somehow fluctuated because the sample size is small. And I also posted one web link which explains the consequence of small number clustering because I found it, but yeah, I didn't do any thorough search. So you may find better explanation, but yeah, I just found it and then they are not telling a lie. So I just posted this link for your information. Up to now, do you have any question? Okay, no. And we move on. So the next thing is how to assess mean component. And I mentioned that in this study, we are interested in age, sex, and population size. And here we are looking at the BMI versus the association between age and BMI and age. And this is just a scatter plot, men and women. Well, we can see kind of somehow by eyeballing the BMI increases as age increases, and after 60 maybe it's going down, and somehow difficult to see the difference between men and women with this scatter plot. But we can see that some outliers, BMI above 50 here, and there are some points with BMI above 60. So this one also we want to keep in our mind, but I don't think all these are outliers, but I have seen people with BMI of 100. So I think these may not be, not the error, but it's possible. Then we superimpose lowest curve. I hope that you're familiar with this lowest curve. This is a good method to see crude trend between variables. And well, we see what I explained, the BMI increases as age increases and goes down later for both men and women. And it seems that there is a difference between men and women. But we cannot see the difference much because of these outliers. The scale is somehow, I should say, it's from 0 to 100. So let's look at only these lowest curve. So this is a 1. Now we see some difference men and women and going up and down. And the next question is, well, now the association between BMI and age, they are not linear, obviously. And the next question is how to model. So usually there are two approaches. One, we use quadratic term so that we can model these curvature. And it may fit well, this observation, but there are drawbacks. One, when we want to interpret coefficient, it's very hard to interpret coefficient of quadratic term and single term. And the other thing is, well, for women, it may fit well, but for men, here we see some steep increase, and then afterwards, dull decrease. So the inclusion of quadratic term may not work well. And the second option is we use categorical variable, or we divide ages into several age categories. This is another way, and it's which is quite popular among investigators, since the interpretation becomes much easier as compared to quadratic term. So here I decide to use a categorical variable of age. And this is a graph. Well, I used a 10 years category, 20 to 29, 30 to 39, and so on. And here is the association I see between men and women, and it seems that the difference between men and women start increasing as age increases, and here there may be significant difference men and women. And let's move on to the next covariate. So next covariate is population size. And well, this is a distribution or scatter plot between BMI and city population size. And you note that it's skewed. Here, well, we see some clouds of cities with moderately small number of size. And then we have one city which has huge city population size. Well, when we do regression analysis, it's okay that predictors or covariates follow normally. It's not necessary that they are normally distributed. It's not necessary. But we have to be careful with these are skewed data sets because these parts can influence the estimation of slope a lot because it's far away. When the observations are far away from the mean, it's going to affect the estimation slope a lot. So what do? We use transformation, and usually we use log transformation. And let's look at log transform value. And I plot the same data set using, well, now X scale is in log scale instead of normal scale. Well, still this city have somehow larger city population, but now the observations are scattered around much better than previously. And how is association? As we did, we plot lowest curve. And well, at least we can assume that there's a linear association between city population size and BMI. But unfortunate thing is that I don't think city population size affect BMI. This is what we can see from this plot. So summary about mean component. So it's to check the pattern of association between the outcome or response variable and covariates or predictors. And main purposes are, one, to know the data as the same as previously, and to identify outliers. Third, to know crude observed or an adjusted association before fitting model, which is kind of important. And the modeling doesn't help. I mean, if you don't see no association here, it's not that likely that we are going to see very significant and strong association after model fitting. Well, the association might change, but not that much. And if you see such changes, you may have problem in data processing or data structure itself. So this is quite important. Also, this is to find more suitable method for the study, well, including how to accommodate nonlinear association between outcome and predictor, outcome and covariate, and also skewness of covariate, and also distributional pattern of the outcome response. Well, this one I forgot to touch that much, but when we look at the BMI distribution, BMI tend to be skewed a little bit, and we see higher value as compared to lower value. And usually scatter plot or box plot would be an option for this assessment. But I think you understand that this is very similar to what we do for regular regression analysis. Does anyone have any question up to now? Okay, no. And again, feel free to interrupt me in the middle if you have a question.
Goro?
Yes.
The second graph you had showed, yes, this one is the city size population log transforming here?
Well, the value itself is not log transform, but the x-axis was, you can see, well, it's log. I use log scale.
Okay.
This is 100 and this is 50 and 25, so it's not actually. Well, here we have, well, the distance between here 10 and 100, 100,000, they are equal. So it's log. So it's kind of a log transformed way of looking at the data. But when we start modeling, of course, we are going to get a value which is log transformed when we fit the model.
Thank you.
You're welcome. Well, so instead, well, here I use log scale instead of usual scale, but you can also do so where you can calculate logged city population size, and then you can plot it this way. And I plot this way because sometimes when I was told 10 logged city population, I cannot tell what it means. So this is the reason why I change x-axis into log scale instead of using logged city population size. But we are going to see the same thing. Thank you for the question. So let's go to now variance component. So this one shows the distribution BMI by city. And the question now here we have to assess how if the variability changes across cities. And I mentioned that we have to look at between city variance and within city variance. How to do that? First of all, we look at this median part, which is this bold black line. Oh, well, by the way, because we have these outliers, somehow it's difficult to assess. So we are going to truncate the data at 60. And this is a same box plot, but when BMI is above 60, it was truncated at 60. And so we want to know if these median, how fluctuate these medians are to assess between city variance. And I added lines which shows a minimum and maximum median as a proxy of to see variability between cities. And samely, I superimposed the minimum and maximum value of BMI, which indicates the variability within cities. And as you know, well, here we truncated at the value at 60. So this blue line should be much higher. Okay. So from here, we can see that between city variability should be much smaller as compared to within city variability by looking at the width between these two red line and between these blue line. And next thing is we need to know if the variability of variance is somehow constant across cities, because this is the assumption we use. And to do so, we look at IQR, well, which is given by the difference between the edge of box. And this one is a third quartile, and this one is first quartile. And we want to know if this width of IQR changes across cities. What do you think? As a constant or as a different? I think they are somehow different. And here, I think this is city 20, we have big IQR. And city 35, we have very small IQR, and others somehow, well, more or less in between. But here we have to recall that some cities have very small number of observations, like 7 or 10, or many cities have less than 50 observations per city. So we have to consider about it. And now I extracted only IQR in the next graph. Well, this is IQR. And also I superimpose number of observations using line plot. So let's look at this one. These these two bars or two cities, which is indicated by these red arrows. City 20, well, which has observation 7, the IQR is the largest among cities. Well, it may be possible that it's just because of small sample size, and the sample was not that much representative, so IQR was big. And the second one was second smallest city in terms of number of observation. Well, IQR is about 12, which is also high as compared to others. And let's look at the opposite direction. Two cities which have somehow big sample size. Cities 58 have about 950 observation, I think. And the IQR is about 7.5. And I assume that this IQR is somehow more accurate as compared to other cities because of the larger sample size. And second largest city, which have sample size of around 650 or 250 or 200, IQR is similar. It's about 75, between 7.5 and 8, I think. And in between, well, we see fluctuation. And let's look at these two variables, IQR and number of observation per city using scatter plot. And it may be clear that, well, when we have, well, by the way, y-axis shows IQR and x-axis shows number of observation per cluster. And well, when we have large number of observation, IQR is around this area, between 7.5 and maybe 8 or 9. But as sample size decreases, IQR started fluctuating. And then when the number of observation is very small, IQR was big. So from this information, well, when we look at that box plot, when we look at the IQR, the width was somehow fluctuated. Maybe my conclusion is maybe it's just because of sample size. So I assume that the variance is constant across city, and I go on to model this data set. So the summary about the variance component. This is to check again between cluster and within cluster variation of the outcome or predictor variable. And the main purpose is, again, this is to know the data before we start modeling. And second, we try to know the crude, observed, or unadjusted between cluster and within cluster variation of the outcome or predictor value. And thirdly, to assess if the variance of the outcome predictor variable is similar across clusters, because this is the assumption we use when we model mixed effect model as well as GE. And usually scatter plot or box plot stratified by cluster would be an option for the assessment. I wonder if you have any question about variance component. Okay, no. Okay, let's go on to the shrinkage, it seems that not many people heard about this shrinkage. And whenever we use mixed effect model, this shrinkage always happens. So it's nice to know. And this time, just to be simple, well, our model included BMI as outcome variable and age, sex, and population size as covariate. But this time we take out all covariates. We think about intercept only model. And to estimate city specific means. And when we calculate city specific mean using mixed effect model, these estimates are called empirical Bayes estimate or best linear unbiased predictors, which is called BLUPs. And I wonder if you heard these terms. If not at all, that's fine. And I just want to tell you this terminology. And the model equation is this one. BMI of person J in city I is given by beta naught I, which is a city specific intercept, plus residual, which is a difference between individual BMI and city mean. And this city specific coefficient, beta naught I, is decomposed into two parts. Beta naught, which is a overall mean across all the city, plus random intercept, which is a difference between overall mean and city mean, plus residual as previously. And well, when we fit the mixed effect model, we assume that this random intercept and residuals both follows normal distribution. And this is the reason why this model is sometimes called two-stage normal model. And now we are going to compare city-specific means from mixed effect model, which is beta naught I, with observed city-specific mean for BMI bar I, which is given by maximum likelihood estimation. Well, I think many of you heard this term maximum likelihood, but what does it mean? Well, it means that we calculate BMI by averaging, meaning that if the city have 100 people, we add up 100 BMI and we divide by 100. And this is a maximum likelihood estimation. It's usual mean or usual average. So this is a plot which shows city average BMI calculated by using maximum likelihood method. And again, this is the same as the mean or usual average. If there are 10 people, we add up all 10 BMI and divide by 10. And well, they are fluctuated by city. And in the middle, you see overall mean, which is shown by black line. And now we are going to fit this model, which is a mixed effect model. And we try to estimate B naught I, which is a city mean, according to mixed effect model. And the red dots, this shows estimation using mixed effect model. Or as I mentioned, this estimate is called empirical Bayes estimate. Again, in other words, estimate given by mixed effect model. And well, let's look at city one. Well, this is an actual mean. And this empirical Bayes estimate is somehow different from this mean, but this mean shifted towards the overall mean. And the second city city 2, this is a observed mean, and this is an estimated mean from mixed model. And city 3, well, this is an observed mean, and this is an estimated mean. So when you go through, you get to know that estimated mean, city mean by mixed model is always being shrunk towards a overall mean. And this is the reason why we call it shrinkage estimation. And why does it happen? It happens because these ones, the red point, these are calculated as a weighted mean between observed BMI, observed city average BMI, and overall mean. And this is the reason why we see these red dots between blue dot and overall mean. Okay. So why does it happen? Well, if you remember, we have different sample size by city. And the question is as follows. Now we want to know the city specific mean of BMI for each cities. And I have cities from which we get 7 people in our sample. Do you think we can get an accurate city estimation? The answer is maybe no. I mean, there are many people in the city, and I have only 7 people from the city. Does the city mean, observed city mean, is close to actual BMI mean of the city? Maybe the answer is no. So here, since my city belongs to these are all cities, we want to borrow the information from other cities. And this is the reason why this red point is calculated as a weighted mean between observed mean and overall mean. And well, I pointed out these 2 cities where we had sample size of 7 and 10. And you can see that this estimated mean is very close to overall mean because it has very small number of samples. And when we look at the cities that had large number of samples, well, 58 had more than 900, and city 50 had more than 200. So the proportion of decrease is much smaller as compared to these cities because the sample size is big, and the estimate should be more accurate because we have more sample size. And I plot this graph using, well, scatter plot. Horizontal axis shows observed BMI, which is calculated by maximum likelihood method, which is again just a simple mean. And vertically, we see estimation given by mixed effect model. And as you can see, say, for example, well, this city had mean BMI of 32, a little bit above 32. But when we use mixed effect model, their estimation was somehow below 30. And cities below 60, well, this is a observed mean, but estimation from mixed effect model is about above 28. So it's shrunk. And this is the same plot, but I use circle. Big circle mean larger, well, city with larger sample size, and small circle mean city with small circle, well, small sample size. And as you can see, well, for example, here, these circles larger circle are close to this identity line. And again, here, larger circles are close to identity line. So what I want to say was that if the number of samples, the sample size is big within cluster, the estimated city BMI is going to be somehow close to observed BMI. But the sample size is small, there the estimated city average is going to be much closer to overall average as compared to observed BMI per city. Marianne, do you have a question?
Yes, Goru. So if the shrinkage estimation is closer to the overall mean, we could, it makes sense to think that the variability between cities, BMI cities, will be lower. So we will have a less heterogeneous sample. So when, for example, modeling BMI with other covariates to check association, we will have we have an estimation of those associations of covariates and BMIs with a less impact, like lower estimations, like the magnitude.
When you say magnitude, are you talking about the variability, or are you talking about, when you say magnitude, which magnitude are you talking
about? For example, if we use odds ratio, prevalence ratio, or RR, like what we will, the indicator we will use to make the associations.
That one, I don't think these estimation will be affected by this. It will be affected, well, when you are interested in this ICC, which I'm going to talk about later. So the within city variability is going to be smaller than as we saw. So there will be some difference between when we assessed using the box plot, which we did previously, and when we actually calculate ICC from mixed effect model, we may see the difference between them. Do you have any question? Okay, this is about shrinkage. And next is, okay, the shrinkage estimation, where maximum likelihood estimate is given by an average of all observations within the cluster, or which is usual mean. And this empirical based estimation is given by the weighted mean of the MLE, maximum likelihood estimate, estimated city mean, and the overall mean. So for clusters, or in our case, for cities with small number of observation, we borrow information from other clusters for more accurate estimation. And for clusters with large number of observations, we have good estimate for city, and we don't need to borrow information from others much. And this weighting depends on the cluster size as well as relative size of between and within cluster variance. Was the last component this part I didn't explain because I need to go to the formula, which I don't think it's necessary. Then let's go to ICC. And now many graphs, by the way. I plotted residuals and random intercepts in this graph per city. What is residual? Again, it's a difference between actual BMI and estimated fitted value, which is estimated value or fitted value, which is city specific mean, okay? Which is represented by this gray dot. And you see pink dot, which is a random intercept. What is random intercept? Which is a difference between city specific intercept minus overall mean. Okay. And I superimposed estimated plus or minus 2 standard deviation. So this pink line shows the variability of random intercept, which is an indicator of between city variability. And this plus or minus SD shown with blue line, this is a let's say kind of indicator which shows within city variability. And by looking at this one again, between city variability is much smaller as compared to within city variability. And how to calculate ICC? Well, when we ask statistical package, what is ICC, it will calculate it. But yeah, anyway, so this is a result, but when fit this model, intercept only model, and this is overall mean 28.8. And this one is a variance estimation for random intercept, and 39, this is a estimation of variance for residual. And the formula for ICC is this one, variance of between cluster variance divided by total variance, which is given by between cluster variance plus within cluster variance, which is equal to variance of random intercept divided by, well, variance of random intercept plus variance of residual, which is 0.01 in our case, so which is quite small, meaning the variability among total variability we see in our observation, 1% is explained by between city difference, and the rest of 99% is explained by within city variation. And just to be familiar with ICC value, this is an example. Well, this is a toy example. I made a simulated data for 20 cities, and both of them have the same within city variance, but different between city variance. Here, this scenario, you see, well, when you look at the median of each city, they fluctuate quite a lot. And in this scenario, we see less fluctuation between cities. And which ICC is going to be higher than others? Then, well, this is the ICC. Well, here ICC is 6.3, and this is 0.04, because when the fluctuation, when the between cluster variance is high, ICC is going to be higher. So, and this is what we expected. So, summary of today's session. We reviewed method for EDA, and which is applicable for both mixed effects and GE model. And we went through how to assess these 3 components: clustering structure, mean components, and variance component. And well, this process is necessary to understand data better. And if you understand the data better, we can think about more appropriate models that fit your data. So which is quite important. And usually graphical assessment generally helps. And we also covered shrinkage, in which borrows information from others when the cluster size is small. And we also covered ICC, and the higher ICC, the higher between cluster variability is. So this is the end of today's session, and I wonder if you have any questions. No. Okay. Thank you very much for your participation. And next topic is going to be a model checking with a linear model. I had some comments from some people how to do model checking after we fit the regression model. So we are going to cover this topic, and also as well as some topics when we model. And but yeah, the reality is we don't have many things we can do for model checking in case of mixed effects model. And if we have more time, we will move on to the case of logistic regression instead of linear model. And we are going to meet on Thursday, September 9th at the same time. And if you have any ideas about topic to be covered, please let me know. And this is the end of today's session. And thank you very much for your participation.
Thank you, Guru.
Thank you, Goro.
Bye.
Thank
Thank
you.
you,
Bye
Guru.
bye.
Bye, Goro.
Thank you, Guru. Bye bye.
Bye, everyone.
Bye.